thing.
I think we can start with stuff. So it's a truly a pleasure to introduce Sambuddha, who has a very illustrious background, TIFR PhD, strongly correlated systems, then multiple postdocs in very good places, and he's an inspired faculty and also a manager. So it's not you can see the kind of talent he has. Now you can see one more thing is that in any type of quantum correlation you look for, they all appear in magnetic systems. And you can see quantum spin liquid, frustrated magnets, disorder systems, all these places he has a link. And this strongly correlated many-body quantum physics is the place where quantum correlation can be tested. To my good luck, when I came here, my colleague Chiranjeev Mitra, he had a good sample from copper oxygen sample antiferromagnetic system from Professor Swadhin Mandal. So from there, we started seeing the correlation of concurrence, connection with susceptibility, then discord. And I am very happy to say that I was part of one paper where the manifestation of quantum discord as a function of temperature and magnetic field in an antiferromagnetic physical system truly showed up. Then later on, of course, there are theoretical works. So magnetic and, for example, right now, almost all the quantum computers, they're built on the principles of Eisen's spin chain. So therefore, this would be a very timely discussion and, very beautiful background where you can truly see manifestation of quantum correlations. So without much ado, I will leave the stage to Sambuddha. Sambuddha, you can take, I think, 45 or 50 kind of things. Okay.
Yeah, that is good enough. Okay, thanks a lot to Professor Panigrahi for giving me this opportunity to talk here. And it's a long time I was thinking of doing some interaction with you in some form. So hopefully it will start from here. And yeah, it's nice to see all these students and to attending this. So I will I changed my mind that how I start my talk based on Professor Panigrahi's nice introduction. So let me say a little bit about like what he said about magnetic systems that are the one of the best places to start all this looking at this, and that's indeed true. And the simple reason is the fundamental building block of quantum computing or any of that sort of thing is basically your device, whatever sort of device you want, are basically qubits, and which is basically two-level systems. And two-level systems can be at many places. But the most commonly and most abundantly, the two-level system that we have around us are spin systems, spin. Right? So not so surprisingly, that a spin model or a spin system is basically the most natural starting point. The most natural starting point to think in terms of when you want to have a physical realization of any ideas in quantum computing and or quantum devices. And one more good thing is that this subject has a somewhat long history, and therefore people know a lot about this kind of system. And in spite of that, there are a lot of things which are yet to be known. And so let me tell a little bit about the experimental front, because as he mentioned about this experiment in Chiranjeev's group, that indeed in experiment there is a lot of control right now possible on this spin system. So one can literally engineer an Hamiltonian in cold atom systems. Not yet in solid state devices, but probably somewhat close one can go. That one can tweak a Hamiltonian and all that. And one can literally engineer a Hamiltonian and control almost all of its property. I mean, to some extent, not to that, like everything you desire can be done, but whatever something, I mean, what you imagine cannot be done few years back is not now getting done. So it's a very rapidly progressing field, that I would say. And as far as solid state devices are concerned, there are also very interesting progress. That, for example, one I'll just briefly mention that there is a great scope of like some theory experiment synergy there, because a few years back, I don't know if you heard, I believe many of you heard about it. There is this model called Kitaev model. So what this model was, Kitaev literally cooked up a model which can be fermionized. It can be fractionalized in the sense that you can write the spin degrees of freedom in terms of other fermionic degree of freedom. And he cooked up the model in a way that it is exactly solvable. So after you normally you can fermionize any model, but if you do that, the model you get is not easy to solve. But he set up the model in a way that the model you get is a quadratic and easy to solve model. And it has loads of features, lot of features that you want to study, like spin liquid and stuff. And that's why it became like a harmonic oscillator model of the community. But in another few years, like less than 4 years, people found a material. It's called sodium iridate, and now there are many materials, ruthenium chloride and all that, where that model can be realized. So even though it's an artificially constructed model for the purpose of building a harmonic oscillator kind of idealized system that can be solved, it turns out that it can be. It turned out a few years later that this model can be realized in experimental system. Not exactly in the form as it was envisioned, but that form with some perturbative correction and sometimes non-perturbative correction. So the point is this field moves so fast and moves in a way that the theory experiments are very close. That you can imagine that playing with toy models in some sense is like a very productive thing to do here, at least, because it's first of all, Hamiltonians can be engineered in cold atom, but even if it cannot, there is a high chance that your model will be there. There is some chance, not high chance, because K-type models phenomena
sorry,
doesn't happen.
we see your first slide.
Yeah, I'm not changing slides. I'm
okay.
just talking about.
Second comment, we see your picture on the top of your slide in the right below corner. Sorry. So we do not see fully screen.
Okay, so what can I do about it? Should I? Oops. Can you see my screen again?
Not yet.
We see only video, but we don't see slides.
Okay, just a second. Let me do that again.
You have small window, your videos, you can take out that. We already have that small part of the from the Zoom. You can take out your that.
Okay. Yeah, I did that.
No.
Yes. I think that is, this is good now, right? Okay. So what I was saying that even though it is not a typical example that you construct a model that it will be realized at a material, but there is always, it is possible that you can play with some toy model which are close to realistic systems, get some non-trivial physics out of this. In fact, this is one of the spirit of this subject, that you construct the minimal toy model that captures a particular phenomena that you want to study, and often that toy model turns out to be, and also sometimes how you construct it is very close to a real system. And in case of P-type, that was like miraculous, that it was almost that is what he constructed turns out to be a real world model. Okay, so I will today in this talk, so this is just to set up the importance of this kind of spin system, where a wide range of exotic phenomena can be realized. And there are, I will come over the course of this talk, something really like the spin systems are literally like a model of all possible kind of physics you can imagine. Even if you think of the synergy between high energy physics and condensed matter physics, many developments, many idea came from Ising model, and like renormalization group and idea of asymptotic freedom, they all came from this kind of studying spin system. And today I will talk about one example, which is like, you'll see that meson-like excitations in spin system that are very interesting in this context, in the context of this talk. Okay, so what we will talk about today is dipolar linear in hole-doped collinear antiferromagnet. And don't worry, my introduction of this talk is basically unpacking this title. And all these are keywords, and I will explain in my introduction, be constituted explaining this. This work can be found in archive and with that name, and it is done in collaboration with two of my friends. They are postdocs at Stanford and MPIPKs, John South and Alexander Whiting. And I've been generously funded by DST SARP and internal funding of IISER. Okay, so let me give you quickly the gist of the story, the whole background of the story, and more importantly, explain you all these terms that I have been, all the keywords in the title. So first of all, let's understand what is a collinear antiferromagnet. So a collinear antiferromagnet is something of an antiferromagnet on a, let's say right now I'm talking about honeycomb lattice, but it could be any other lattice, where the spins are arranged in this way, that along this bond they are all same, pointing in the same direction, and along the, so let me call these bonds the Z bond, and this bond the X bond, and this this bond's the X bond, and this bond the Y bond. So along a Z bond they are oriented in the same direction, and along the X and Y direction bonds they are oriented opposite direction. They are antiferromagnetically oriented, and in Z direction they are ferromagnetically oriented. So that's the definition of collinear antiferromagnet. You might wonder that why do I start with such a strange thing? I'll show you that there are models for which this kind of a order state is the ground state. So this is the first thing we need, and then we talk about hole doped. Hole doped means I'm going to dope a hole in this antiferromagnet, which means I am going to eliminate a spin, and that in real world that is equivalent to doping a non-magnetic impurity. So let's say this copper oxide kind of spin system, that is equivalent to doping that copper by a zinc and so on. Okay, so or something else that is is going to get rid of this non-magnetic impurity. See, non-magnetic get rid of that spin. It can be also physically knocking off the site. Okay, so that here I am going to talk about now what is dipolar linear. So first I talked about this one hole, and then I will talk about two holes. Two holes means I'm going to dope this system with two holes, and I'm going to show you that something interesting is going to happen when I do that. Okay, so then let me talk about what do I mean by what is the main essence of this work. So what my ingredient of this work is basically a hole doped Ising magnet. I have this kind of a magnet which is all the spins are oriented in the spin Z direction, so they are Ising in some way. And I have this hole that is hopping in that. So this kind of model is called TJ model, and they are the classic setup to study something called, if you heard about this, these are classic setup to study high TC superconductor. For a long time, it was believed that, I mean, believe means it is experimentally true, but there are controversies on the theory that if you dope a Mott insulator, you get a high TC superconductor. That is at least true for cuprates. And then one can try to understand that kind of system by a magnetic Mott insulator and hole interaction. So here I will not go in that direction. I am just telling what is the history of this kind of models. So what do we need? The second ingredient we need a non-degenerate ordered spin model with local two spin interaction. So I will show you the model in the next slide. So the model I require, I am going to work with is a local model. Local model means the spins only interact with its neighbor. There is no long range interaction or anything. And they are two local, which means nearest neighbor, not forced interacting or something like SYK or some or kind of model. And the third thing is important is going to come is the interplay of geometry and exchange interaction. This particular geometry is important. This honeycomb geometry and interaction form is important in this model. And the fourth thing I will show is that this is true in the both, whatever result I am going to discuss is both in strong and weak coupling limit. So what does that mean in this language? It means that T can be greater than J and J can be greater than T, both limits. So one limit I will show perturbatively. The other limit is hard to do a perturbation theory, so I'll do an exact calculation. And what I'll show that these things can be true in both of these true limits. And finally, I will show these results are almost exact. By that I mean they are true. Whatever result I'm going to claim are going to true up to very high order in perturbation theory, and that's why I call them almost exact. And this is basically my ingredient and the main result. So I will give you the main result, the punchline, and then I'll try to convince you that why it is true. So if I have a system with this kind of this constant, what I'll show that I can dope a single hole in that system, and that single hole will be completely immobile. It cannot go anywhere. It will be completely confined. Okay? But if I dope two holes, then I'll show you that two holes can move only in this direction, only in the XY direction in this picture, not in the Z direction. It cannot move in the Z direction. That is the forbidden direction. So why do I care about such a thing? So these kind of things are and okay, one more point, important point I missed, that I will also show that these two holes have to be always together. They are bound. They are somewhat like mesons in a quad. That you will see that if I try to take them apart, I have to pay more and more energy. But if I keep them close together, then they are like they are the lowest energy state. And so that means an isolated hole is completely immobile in this 2D system, and a pair of hole is mobile only in one direction, not in the other direction. So somehow the system will have a unidirectional subsystem symmetry, a transition symmetry only in that one direction, and the other directions symmetry is spontaneously broken. A more sophisticated way to tell that is that the system will have an emergent dipole conservation. So I will define that, how to define dipole moment in this system, and define dipole moment and charge. But when we'll do, we'll see that the original Hamiltonian doesn't have a dipole moment conservation, but this effective low energy physics of this system, where a pair of hole can move only together, not in isolation, and it can only move in one direction, that has a dipole conservation. So it turns out these kind of systems are very interesting in recent times. They are called fractons. So fractons are basically systems or degrees of freedom that have fractional mobility. That's why it's called fracton. So there are two types of fracton. One type is completely localized. They are called type 2 fractons. Another type is no matter what you do. Another type is they are localized if in isolation, but mobile when they are together, when they form a bound state. So this is that type. This is the type 1 fractal. And not only they are mobile, they are mobile in a fractional subspace of the original problem. So that's why this name came from there. Fracton name came from there, and they are believed to be topological excitation. So topological excitation means they have some underlying property that by any local change in the Hamiltonian, you cannot change whatever that property is. Right? By doing any local deformation, you cannot do anything. So they are believed to be topological, and they are considered as very important idea because, as you know, like let me go a little big picture side, that the whole technology that we are using now, right now, this talk is happening through a tremendous progress of technology, right? So electronics and stuff. And that is based on the fact that an electron or electron-like object is the main carrier, is the main degrees of freedom that is carrying charge. And that is the transport. And then you make various devices by giving various potential gate and all that, and come up with all these applications, right? This is the fundamental ingredient, is your ability to control and manipulate electrons that are carrying charge, right? But this idea, so now we are heading towards something called quote unquote quantum technology. Because it is a little mistitle, because this is also quantum, like because electron gate and all Fermi surface and all this is also quantum. So what I am doing is not like that is also like quantum. So it's there is no need to call it separately quantum technology, but quote unquote, this is what we mean by quantum technology, that goes beyond this paradigm, that just an electron or electron-like objects being manipulated. So one aspect of this, there are many facets of quantum technology. One aspect is when the main degree of freedom or main carrier is not an electron. It's either a pair of electron in a fractional subspace or something even more exotic, that is a fraction of electron. So that is a subject that could be a subject matter of a different talk or different discussion. They can be seen in a spin liquids. So in spin liquid environment, it's a many body entangled system where you can show that a electron behaves like as if it is made of fractionalized subsystem, fractionalized subparticle. They are called partons or spinons. Okay. So that's a different story, but this is also a different aspect. But what is common between both of these two? They are both has topological origin, in the sense that in a crude sense, of course, topological origin, that word can be more rigorously defined in a mathematical sense also. But let me, for this talk, just use a crude sense. It implies that a local deformation in the system or in your problem cannot change the properties that you are talking about, the main properties that you are interested about. They are all global properties. Okay, so this is the punchline. This is the whole punchline of this problem. Now let me go to the details. Okay. So so let's first start with the idea that how I can think about a hole in an antiferromagnetic background, in a spin background. So the idea is very simple. Let us start with this Ising antiferromagnet. Ising antiferromagnet means spins are oriented either up or down. There is no other possibility. Okay. Now let us say I dope a hole. I dope a hole in this system, and that hole, and that hole will move like this. And when it moves one side, when it moves from here to here, then this downspin will come here, right? But this downspin will frustrate the system. Frustrate the system in the sense that now this system wants every spin to be anti-aligned, right? This is this model, JJ, SI, JSJ. If JJ is positive, you want the I and J in neighbors to be up and down, plus and minus, right? So if it is down, if J is negative, then you want them up, 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 then it's a ferromagnet. Okay. So the system wants all the spins to be anti-aligned with its neighbor. But if I put a hole and let that hole move, that thing is broken. That thing is broken at least at one point, right? So then the system is not happy. It's happy in the sense, I use the word happy. It means it's energetically not at the lowest configuration. So then, so that is kind of not a process that the system will like. Okay. So let's like carry through this idea and see how do I describe this? How do I make a theory of this problem? Okay. So my ground state can be thought of as some product state initially of all these up and down. So CRI down and CRI RJ up. If you are familiar with this notation, it's great. But if you're not, just think that if you have taken a quantum mechanics 1 course, you know about creation and annihilation operator. So these C operators are basically some creation operator. It tells you create a spin of up spin at location, this location, and create a down spin at this location. And I am saying A and B, I am calling them A, B, A, B. And I am calling put all A's with up, and put here I am saying put all A with down. So it should be B, A, B, A, and put all A's with up. Right? So that is basically a simple description of this system. Now I introduce a notion that I want to delete a spin. I want to put a hole, right? So then I should annihilate that hole. Now this annihilation operator, I can represent it with another creation operator, which I call F, that is equivalent to creation of a hole, which is so creation of a hole is equivalent to annihilation of a spin, right? So that's why this equivalence. And annihilation of a spin minus is equivalent to creation of a hole plus. That is basically just to preserve the magnetization. So that is how I set up my problem. Okay. Now notice that if this spin is moving, which means I am deleting a hole here and creating a hole here, right? So that is like saying I'm deleting a hole here and creating a hole somewhere else, like just in neighbor, not somewhere else. And when I do that, I flip a spin. I flip the spin that is supposed to be here originally in this location, right? So that should be represented by some sigma minus and sigma plus operator. A minus will do a minus and plus, their job is to flip the spin. Okay. So they will flip the spin, and if you look at the algebra, it's bosonic algebra, they have a commutation relation. So I can replace them by some bosonic operator. So this process where you start with a spin state and a hole, and you end up with so you go from here. This is your initial process. This is your initial. This is your final. Right? One hole moves, and your initial picture is you have a certain spin configuration with a hole. And the next picture is the hole is moved in one side different, and original position of the hole where the hole was, now you have a flipped spin. This picture is captured by this Hamiltonian. So you can describe this picture by this Hamiltonian, where this process is given by this. You delete a hole, create a hole, and you flip a spin. Right? So this is this, and you have to make it Hermitian, of course. So this is basically the model. This is the model I'm going to work with. And what I can now let's so I will go back and forth between models and picture. One good thing about this problem is that without doing any calculation, you can have a rough conclusion about this problem. But then, of course, you have to do a calculation. So I will show you, we did up to 14th order of perturbation theory to reach at a concrete result, that if you want the numbers, that what is the probability amplitude of this process, you have to do the calculation. But if you want to grossly say what will happen, then you can go by pictures. So for the purpose of the talk, I'll mostly go by pictures, but know that every picture every word written has a calculation behind this. Okay. So let's go to the picture again. So this picture, I told you before that I have a hole, the hole dopes by one side, and then you frustrate one spin. One spin gets at a position where it's not supposed to, which it doesn't like. Right? Now see something very interesting. If I put two spins, if I put two holes, okay, so then this hole can move, a down spin can come here, and then this hole can also move, right? This hole can also move, and then this down spin goes here, and you are left with a spin configuration that is not frustrated, which means all neighbors are anti-aligned. Okay, so now notice what happened. If there is one spin, if it wants to move, if there is one hole, it wants to move, there is no way other than by frustrating one bond. But if two holes want to move in this way, that one goes and then another one comes, one goes, another one comes, like this, what I call this amoeba movement. Okay, I don't know, I forgot the biology term, but it is basically this one step movement. If it moves like that, then this whole pair of hole can move without frustrating the background. Okay, by healing, it can heal the background. So I'll show you what does that mean. So now you can do also another thing. You can take also these two holes apart, right? So these two holes are not very strongly confined. They are kind of weakly confined system, and they can be taken apart also. Okay, and also you will see here, you have done one hopping, but if you do the next hopping, then you will get this. You'll do this, you'll get this. So it's only the first hopping that is frustrated. After that, you can keep going. That is not frustrated. Okay. So you can actually describe this by an effective Hamiltonian, and this effective Hamiltonian is given by. So how to do this effective Hamiltonian? I will just give you a 2-minute overview. So the idea of doing this kind of effective Hamiltonian is that you start with this H psi equal to E psi, the full problem, where H has two parts. One is H naught plus V. In this case, the V part is basically this Ising part, and H naught part is this hopping part. Sorry, the V part is this Ising part is the H naught, and V is the hopping part. And then you can split your full Hilbert space into two parts. This P and Q are the projection operator for this part. This is the general rule of projection operator. And then you can split the problem by inserting this identity twice. And you can work out this by 2-3 steps of algebra. And you can get an effective Hamiltonian that is projected into the subspace. And that subspace is basically the subspace with no excitation, no frustrated bonds. Okay. When you do that, you get such expression. This expression can be arbitrarily up to large order. Now, if you say your V is weak, your V means the hopping. If the hopping is weak, then you can truncate this series and do a proper perturbation theory. So this is the idea of doing that. So in this case, I have assumed my T is weak. T is weak means this is my, so this term is my H naught, and this term is my V. Okay, so this V is weak when I take this limit. So I can do this perturbation theory and work out the effective Hamiltonian. And what I get is basically a number term, which means there is no hopping. Okay. But if I put two holes, so this is the constant, there is only one hole. If I put the two hole constant, then the effective term I get is this pair hopping. It means I delete two sides, which is basically these two, and I create these two. So that means I create here and here. Okay, or create here and here. Okay. So this is the idea. And this is, again, the picture can be explained in full rigor by a detailed calculation. That is just the point that I wanted to convince you here. Okay, so now let's keep this side. Let's go what this is just some details that what happened if you include the the defect interaction. So by defect I means when a spin comes here that is opposite to what it is supposed to be, that creates a frustrated bond that I call a defect. Okay, this is just a terminology. Okay, now let's see what happens if I play this game in 2D. Okay. So it's, again, the good news is that everything can be understood from pictures, and then it can be backed up by calculation also. So it is, in fact, that is how I envisioned this calculation, that I first make pictures, I see what are the possibilities, then I do a calculation to show that it is indeed the picture is correct. So let's look at this picture. So I have an antiferromagnet now in 2D, a square lattice, which means it has up, down, up, down, up, down, up, down. All neighbors are up and are oppositely aligned. So now if I put a hole, now this hole moves here, okay? Then you frustrate 3 bonds. Now this hole moves further, you frustrate even more bonds, right? And then you keep doing that. You let that hole move here, you let that hole move here, then let the hole move here, and finally it comes here. So now something magical happens. So after the end of these 6 steps, the hole have moved from its initial position to this final position, and nothing is frustrated in the background. So this process is called a Krugman loop. So this process is a high order process where the hole can travel around the whole loop, and in the process it can heal the frustrated background. Okay? So this is a possibility in 2D, and this possibility is very low, very improbable, because you can see it requires 6 hopping in a particular direction. So if you do a counting that where this hole will be after 6 steps of hopping, you will say like order of 10 to the power 6 possibilities are there. Out of these, one like 6 or 7 possibilities are basically doing this. Okay. So then it's a very low probability process, but it is allowed. Such a process can happen in 2D. Okay. Okay. Now, let me tell you about, refer to a paper which analyzes this problem in great details for square lattice. They call this kind of things a meson-like excitation, because you can see in this picture, so this is the hole, and this hole and this spin, the defective spin, they together form a meson. Okay, you can also think here in this pair of hole is a meson, but this is the language they use. They call this thing a meson, and it says that as you try to take apart this meson, these 2 quarks of this meson, in this case these quarks are basically the spins, then it will create a string of excitation, a string proportional to the distance between these 2. But this is very non-trivial, because there is this Krugman process which says if the string is intersecting itself in certain way, then that string size becomes 0. Right? So these things are called non-linear strings, and there are something called tangential path, and there are something called linear string where it keeps going and when the excitation is growing. Okay? So it's possible to describe an effective theory for this kind of system. And as I explained you, these processes are also like this is like excitations matter only in the t when the t is small, right? When you are in the perturbative limit, when you are in this perturbative limit. So what happens in the opposite limit? For that you have to construct some effective calculation, some effective theory, or have to do an exact diagonalization, a full-scale exact diagonalization. So these people did that, and they have shown for a square lattice, you will see that the hole has a dispersion when the j is much when the t is much stronger than j. Okay, so you can see this value is taken. So jj is small compared to t. Then you see the hole. Then the single hole can move, like, because then these Krugman kind of processes are more feasible. So now let us see another proposal that is also done by same set of authors and some other people also. So what people wanted to achieve for a while, that they want this pair of holes to move in one direction, not in arbitrary direction. Okay, this is one of the condition of fractons. And it turns out you can do that only if you tilt the lattice. Tilt means you make that direction more probable. It's kind of like a cheap hack, but it turns out that is something you can do in cold atoms, and there are experimental papers, etc. People have done doing that. Okay, but what we'll show, you can achieve that without tilting. Okay, so if you of course make one side more probable than other side, then of course this will happen. There is nothing surprising here. But what we'll show, the system will spontaneously choose one direction out of the 2 directions. That is what is unique about our work. Okay, so let's see what do we do. So now I have given all the ground rules, all the basic idea. I'll just play the same game which I have talked so far, but in a more complex setting. That's it. That's the only difference. So what is my setting? I start with a model that is Ising in these 2 directions, in the x and y, x prime and y prime direction. But in the z direction, it's Ising antiferromagnet, but in the z direction, it is ferromagnet. So then again, we are coming back to collinear magnet. We are coming back to a model. So why did I choose that model? Why did I choose this model out of this model? So it turns out that I choose this model because this particular ground state, this collinear state, is the ground state of this model. Okay? Now, this is not the only model whose ground state is that. It's possible that some deviation from this also has this ground state. And that is an interesting question to ask what happens there, that we'll explore in another one. But right now, let's play this game by saying I have a model whose ground state is this collinear magnet, which means it is it is ferromagnetic in this Z direction and antiferromagnetic in this XY direction. Okay? So now I can describe a hopping in this process, in this model. It tells you if it is going in the Z direction, then the hopping is free. Free means it has no defect generation, no flipped spin, nothing, because it's ferromagnetic, right? I can just take a hole and put it there. This will come here, nothing will change. Right? But if I try to move in X and Y direction, then it is like that 1D problem we talked about before. Then we generate some defects. Okay. So this is my Hamiltonian. And what I do, let's just go by the picture, then I'll talk about some more equations. So what I do, I start with a hole. And let that hole move one step in the Y direction, in the Z direction, sorry, in the Z direction. So again, let me draw the Z and X and Y. So this is my Z, this is X, and this is Y. So I let it move by one step in the, so this is actually, it's called me Z prime, Y prime, X prime, because there is a Cartesian X and Y, which I will also use sometimes. Okay? But what I mean by X prime, Y prime, or Z prime are basically these three bonds. Okay? And X and Y are basically your Cartesian coordinate. Okay. If you like, I can choose a better language, but I think it's okay. It's understandable. So then I have this hole, it will move one step in the Z direction. And when it does that, then it has no excitation, nothing, no problem. Okay? But when it goes here, then it gets a bond which is opposite to what is expected to be here. So it makes two bonds, these two bonds unhappy, right? These two bonds gets frustrated. Okay. Now similarly here also, if I go from here to here, right? If I go one side, one step, this Z direction, nothing happens. But from there, if I try to go anywhere, I'll start frustrating the bonds. Okay. So this is basically the game. Okay. So it turns out then here is also a Krugman loop, but it's a 15th order loop instead of this 6th order loop. And this is a bit rigorous, but you can show it by this perturbation theory calculation also. And it's simple. It's not as scary as it looks, but the idea is simple. This hole can hop around this honeycomb lattice twice. If it does it twice, then finally it reaches at a position that completely heals the frustration, that completely heals all the flip bonds. Okay. So now let us try to understand what happens if I put two holes in this model. It's a little lengthy calculation, but at the it can be again explained entirely in terms of picture. So I'll go by the picture. So the picture is following. I have these two holes, and this hole is hopping here. Okay, this hole is hopping here. It frustrates one bonds, right? But then this can go here. This can go here, and then no bonds are frustrated. Just like similar prescription that this can only be confined, and it can move together, not in isolation. If you try to take them apart, then it is costly. Okay, this is also not true in square lattice, by the way. If you try to take them apart, that will cause a string in between them, that as I told you. But what is interesting, that this hole, this pair of hole cannot move in the Y direction, in the Cartesian Y direction. In the Cartesian Y direction. What happens when you try to do that? Let's say I try to take it here and then try to bring it here. Try to take it here. It creates two frustrated bonds, right? It doesn't heal. It doesn't heal the background. Okay. It rather introduces more frustration. Okay. So what is the bottom line? The bottom line is this pair of hole can move only in this direction, but not in this direction. If we try to move in this direction, that creates frustration. So basically, we were able to achieve what these guys were trying to achieve, that letting the hole move in only one direction out of the two direction and localize it in the other, trap it in the other direction. We have achieved that without any tilt. Okay, without any tilt anywhere. And this thing you can describe it. So now you can describe a charge operator. That charge operator is given by this, basically by the spin of this hole. And then you can define, so this total charge is total spin, and you can define a dipole moment, which is charge times the distance. Now this distance between these two holes is constant at low energy, so the dipole moment is conserved. So a more sophisticated is saying that this Hamiltonian has both charge and dipole moment conserved, and that dipole moment conservation is an emergent phenomena here. So in other words, so if you, this is actually a very interesting problem these days, to develop a low energy theory of this kind of system. In other words, a field theory of this kind of system, which is basically you develop a theory that has this extra conservation laws, extra constant, and these are very tricky and non-trivial. So there's it's an ongoing subject of research. It's an active research. Okay. So now now I can do a calculation just like the way I showed you before, some perturbation calculation, and derive the effective Hamiltonian of this system, which describes this same process that I told you pictorially. This term basically tells you two holes are annihilated, two holes are created. A pair is like a pair hopping, but only when the pairs are together. If you take them far apart, that will cost you more energy. Then you cannot get it in the low order of perturbation theory. Okay. So now all this perturbation theory is true when the hopping is weaker than the J. Okay? But what happens when the hopping is stronger than J? So it turns out that for that case, you have to do an exact diagonalization. Then the perturbation theory is very difficult. You can in principle do a perturbation theory in the other way also. But when then the H naught is the spirit of perturbation theory, the H naught have to be simple and the V has to be the difficult part. But in this case, when you try to do it the other way, the H naught itself become very complicated. So what one can do much better is a exact diagonalization. So notice that what happens when you try to exact diagonalization. So let's say I have a n spin system. Okay. So actually there is something wrong here. It should be n minus 1. So if I put one hole, that means I have n minus 1 spin. But that one hole can move there, right? So the Hilbert space is that of the hole and direct product of spin. Okay? So if I have one hole, then the Hilbert space is n times 2 to the power n minus 1. If I have two holes, then the Hilbert space is basically nc2 times 2 to the power n minus 2. So that is n minus 1. Right? Yeah. So that is why this calculation gets so difficult when you are trying to do this many particles. So these pictures are for n equal to this picture is for n equal to 24, but later I'll show you n equal to 32 also. So this is my geometry. This is my geometry of the system. This is my x direction. So gamma, x, and k, and this is my y direction. So if I do an exact diagonalization and plot the eigen values, the band structure, then with one hole, I will see a complete flat band. If you notice here, it's a completely flat band. What does that flat band means? Flat band means there is no dispersion. There is no dispersion relation in that. No momentum dependence. That means it's localized. Okay. So it's a completely local. It implies that if I take one hole, it is localized in all the direction. It's so gamma, m, k, whatever direction you choose, it's all localized everywhere. Right. But if I take two holes, okay, this is the two hole case, then you will see that it is only localized in the gamma m direction here. Okay, only gamma m. So it cannot move in this direction, but it can move in this direction. Okay, so this is the basically what the exact diagonalization tells you. Now notice it's a very non-trivial problem of exact diagonalization. That could be another talk another day, because these systems are like order of 10 to the power 12 size matrices. 10 to the 12 by 10 to the 12. So one uses very sophisticated ideas, exploits all the symmetries, and then use some sort of a heavy parallelization to get through this kind of calculation. Okay, so now we present the same result for n equal to 32, and we'll see the same thing happens. So for one hole is completely localized, but two hole is localized only in this direction. So we added one more point here, and we show that it is completely localized in this direction. Okay. So we tried to play this game with 4 holes also, and we found that something similar will happen. So that means if I put multiple holes in the system, these holes will be mobile in this direction, but immobile in this direction. Okay. So this is basically the idea. And so I'll come back to my original slide just to recap the result, that this is what I told you initially. That was the gist of the result, that if I show you an example of a problem where I start with a particular ordered ground state and I dope it with holes, and I have shown you if there is one hole in isolation, it will be completely localized immobile. But if it is two hole, it will be immobile in y direction, but mobile in the z direction. So this is the gist of our work. And as I showed you, it is true both in the weak coupling and strong coupling limit. One side we did perturbation theory, another side we did exact calculation. And I have also shown you that let me advertise a bit. So this is the first example of a fracton type of excitation, which has this kind of a which can be done in a bilocal model, in a simple bilocal model. If you look at the fracton literature, all models are very exotic and very weird. that has no hope to be realized in a local magnetic system. But this looks like something much more realistic. Okay, so this is the core essence of our work. So I will end with two promising direction. One is immediate. One is something that we are pursuing now. That this idea is that we picked up a strange model, right? We picked up a strange model which we made up that model to get a particular kind of ground state. And you might wonder that how realistic it is. Can it be ever realized in a material system? Okay, or in some, well, you can in principle realize it in a cold atom system, because as I said, in cold atom you can engineer a Hamiltonian. But what about materials? So it turns out that this particular model, this is a Kitaev Heisenberg model. This is a Kitaev term and this is a Heisenberg term. Okay, so it turns out this is actually this model is a kind of a good description of this class of system called Mott insulating iridate compounds. They are called sodium iridate, and there is a whole family of iridate compound. And you can show here that if this alpha is equal to half, then this model is exactly the model that we have done. Okay, and so basically our model is basically one point of the spectrum of models that describe sodium iridate. Okay? But you can ask, what if, of course, when you make a material, you cannot fine tune. If your physics is fine tune dependent, then it's kind of unrealistic. Right? So the good news is that there is a window of phases for alpha, which has this kind of a stripy FM order. That is what we want. So what we expect that whatever physics we are talking about are going to hold at least for this window. And whether it goes beyond that or not, that is something interesting. But this is something we want to now explore, and we are working on this now. Okay, so this is basically one idea to bring this whatever physics I talked about closer to reality. And then I will just give you some overview that what sort of thing one can do here. That it might be useful to have a string picture for this strong coupling limit. But string picture, by that I mean I think of this describe this kind of picture, that I have this meson, in what I call it in that language is a meson, that I can take them apart, it will form a string. But that string is not so unrealistic in the strong coupling limit. So then these strings can be of different kind. In 15th order loop, it will come back to itself, and it will basically become a nonlinear string. So the question is, can one, instead of developing this exact diagonalization, instead of doing that diagonalization, can one do an effective theory for this kind of object in the strong coupling limit? The weak coupling, we already have the perturbation theory, but in the strong coupling, we want some analytically tractable setup. Okay? The next thing interesting is dynamics. The dynamics means you can see how this thing moves. This thing doesn't move just like that, right? It moves one step like that. So it might have an interesting dynamics, even in the absence of any disorder or anything. It is not likely to be a ballistic dynamics. So if I take that object and ask that how long it takes to spread over certain region, go certain distance, then it is probably not ballistic. It is some diffusive or sub-diffusive dynamics. So this is the naive expectation, but one need to check that and do some calculation to see that. Okay. And then there are very interesting, this work is actually, I believe, is a starting point of many ideas, because now you can ask, what if this pair, whatever you call it, fracton or whatever else, what if it interacts with other degrees of freedom of the system? Let's say the partons or something in a spin liquid and so on. So condensed matter is all about quasiparticle, phonon, magnon, all these things. So this is another addition in that lineup, but this is more exotic. But what will happen if it interacts with other such quasiparticles? So this is an idea. And then there is a bunch of cold atom experiments which are extremely close to realizing this kind of model. So what we suggest that within the existing experimental setups, it's possible to realize this model and see this idea in action. Okay. So this is basically what I wanted to see, what I wanted to say, and that's all. So I will stop here. Thank you.
Yeah, now I think the session is open for questions. Really nice talk. If whoever wants to ask, please open and ask.
Yeah.
So anyway, let me start. We had looked at one of the systems where this discord, what was the role of quantum discord myself with Chiranjeev had looked at it, and also specific heat as a function of concurrence. By any chance, have you looked at Discord particularly something?
I didn't look at this point at all, but point is, I believe this model has some topological underpinning, which because I believe if you do something local, because all this whole picture is standing on the structure of this ordered phase. The details doesn't matter. So it has some topological underpinning. So if one looks at some sort of entanglement kind of property, which like Discord is a quantum code, some form of quantum correlation. Right. So one expect to see something non-trivial here. So it is indeed, I think, something interesting to look at, because so this is actually one subtle point also. Normally, so that is why I'm not very strong in claiming this is a fracton. So because the fracton's definition is it has this restricted mobility, but many people wants that to be topological in origin. Now, I have said nothing or showed nothing that says this has topological origin, except hand waving by saying it, okay, because the details doesn't matter. It's only the structure that matters. But if one can show that it has a topological origin or some non-trivial entanglement structure is there by looking at this Discord, and then it will be very interesting. I didn't look at it, but I think it has promise.
Okay. Now, if people are not asking, then I'll ask. How about other people? Please ask. Otherwise, I'll ask one more question. See, that is, for example, this honeycomb lattice, instead of that, suppose Kagome lattice. Somebody looked at Kagome lattice.
So I did all kind of lattices, and finally I landed on these. I decided to write this in the paper because this has everything with least amount of ambiguity. If you do Kagome, it's very difficult to isolate. So Kagome has another problem. It's hard to find an ordered state. So right now I wanted to avoid the fact that the ground state is degenerate. If the ground state is degenerate, so that's why this point is very important. So if the ground state becomes degenerate, a frustrated ground state, then technically it's a hard problem. And I thought I'll do the easy problem first, but it's very interesting and I want to look at it at some point of time.
Yeah, see, the reason I was asking, because this John Simon's theory on this planar Kagome lattice, John Simon's theory finds manifestation, and this like anionic superconductivity, anions, those kind of things may manifest there.
Yeah, so this is actually that's very interesting question. So this is something I want to try. That, for example, you can do this. You can make this brick wall ladder. Okay, some kind of a brick wall ladder. So brick wall is topologically same as honeycomb, right? So well, this is 3-leg ladder. So this is a minimal system. What one can try to see if I exchange two of this part of fractons, the quote unquote fracton, what I call, what kind of statistics I'll get. So this is actually a very interesting question that one can ask here. But yeah, I didn't do anything about it, but this occurred to my mind. And as you said, this could be very interesting.
So my last question is, the square lattice, for example, would maybe relevant for high TC, no? High TC superconductivity.
Yeah, square lattice people have studied thoroughly for high TC. Yeah. But the square lattice is not interesting in this particular context, because in square lattice, a single hole in the strong coupling limit will have a dispersion. And if you want this unidirectional subsystem symmetry, you have to tilt it for pair of holes. So this process, this picture that you don't want the hole to hop because it frustrates bonds. That picture is true when hopping is weaker compared to J, but if hopping is stronger, then it doesn't matter. And in that case, you will get this dispersion. What is cool in our model, so we actually tried a lot of models and finally we landed on this. And now we are trying to justify why it might be realistic or not. That is where this iridate question comes. Then you get this perfect flat band. There is no dispersion in one hole. Okay? And this is 32. N equal to 24, this is N equal to 34. 34 side exact diagonalization with 32 side exact diagonalization with 2 holes. So that's why we are confident that this physics is true in both limits. Although we don't know a mechanism, we don't have a hand waving explanation or mechanism in the strong coupling limit. We have that in the weak coupling limit.
Very beautiful. More questions, please. So if not, then let's thank